Hello everyone. Today we are going to discuss about p-n junction in equilibrium, and I am going to model this p-n junction in equilibrium condition in COMSOL. Um, let the analytical solution for the p-n junction in equilibrium is readily available, and I am going to compare the results with the computational software called COMSOL. In COMSOL, I am going to solve three basic equations. One is uh, drift and diffusion equation in the n side, and drift and diffusion equation in the p side, and the Poisson equation. Here you could see the this is the diffusion term and this is the drift term. Since it's in equilibrium, the condition these are the boundary conditions to be applied. I am going to couple these drift diffusion equation and the Poisson equation in the COMSOL PDE solver. Before that, you should know the graph for the p-n junction in equilibrium. The electrostatic potential in equilibrium has the following graph, and the electric field in equilibrium has this following graph. And let us discuss about the p-n junction equilibrium in COMSOL. First, the boundary conditions for p-n junction equilibrium. The one side is grounded while the other side is given to be 0.578, which is calculated using the donor concentration and acceptor concentration. And this is the p region, this is the n region, where p region contains excess amount of holes, and n region contains excess amount of electrons. And you could see the p region has the equation as follows, and n region has the equation as follows, which I am going to incorporate these both equations into the COMSOL as a variable. We want to obtain these graphs. Okay, let us discuss about this in COMSOL. Okay, I open the COMSOL. I'm going to model wizard. Here I'm going to model it only for a 1D condition. So I'm going to select this as one dimensional, and I'm going to model it in a partial differential equation solver. So go to mathematics, and there you will find a PDE solver in which classical diffusion, classical PDEs. In the classical PDEs, you will find the Poisson equation. Just add it, and up here in the Poisson equation, I give the potential term to be 5. And here the dependent variable unit is volt. So let me electric potential volt. And here the source term quantity, the source term is the space charge density rho, which is coulomb per meter cube. And I entered the after entering the electric potential unit and the source term unit, I am going to incorporate another two equations for drift and diffusion, where I'm going to give the dependent variable p. This is p type, and electron charge, electron density, because here everything was in centimeter 1 by centimeter cube, and here and the dependent variable and the source term variable is the production rate. We consider there is no generational recombination. This term obviously will become source term will be a 0, and another one is for n type. Here the same, That's it. That's it. We have added the physics interfaces into this, and then we go to study. Here we're going to conduct the stationary study. Here you could see I'm going to model everything in a micrometer, and if we model it to be interval of -6, and already I do have entered the basic values like Boltzmann constant, built-in potential, and all those things. I am going to take those parameters into the built-in parameters, and we could see it. And this the mobility of electron un, mobility of holes, diffusion coefficient of electrons and holes, and charge, temperature value, and intrinsic array concentration, and thermal voltage, which is calculated using the Boltzmann constant, temperature, and charge. And and here built-in potential is calculated using the acceptor and donor concentration. Okay, now I'm going to input variables where I do have variables already. This is the P region variable for acceptor and donor concentration. I'm going to select this uh, to be a domain, which is this domain, P region, and I'm going to select another one variable where I'm going to select the domain to be N region, and then I'm going to you could see the values of donor in the N region is higher, and values of acceptor concentration is lower, and the acceptor concentration is higher in the P region and donor concentration is low in the N region. And then I'm going to add some more variables uh, in the P region, where I'm going to enter the carrier distribution, the equation, this equation as a variable, and this equation as a variable. Variable P region, and then I have entered those formulas like amount of holes in the P region is denoted by this formula, and amount of electrons in the region is denoted by this formula. And the concentration also varies in the N region, for which I am going to do another variable, and sorry, um, I wanted to make this too. Okay, now we have defined the variable, and our next process is to uh, denote the Poisson equation values, and we know the Poisson equation is like where the C value I'm going to enter epsilon naught const. This is the permittivity of the free space into 11.8, which is a relative permittivity of silicon, and then the source term is to be Q, which is the charge, into P minus N plus concentration of acceptor concentration plus donor concentration. Actually minus plus donor concentration minus. Okay, that's it. And there is no unit error. If there is a unit error, you could get that in the while entering the terms itself. Then I'm going to enter the initial value, where I'm going to give the initial value to be 0 voltage, and I'm going to give the Dirichlet boundary conditions where I'm giving 0 volt at this end, and Dirichlet boundary condition where I'm going to give this as a built-in potential, which the value is 0.57, which we calculated using the acceptor concentration, donor concentration. Now we finish the Poisson equation. Next we are going to the general form PDE, where I'm going to model it for P region. General form PDE. Here the equation is here I don't want this term, so I'll make EA to be 0 and here DA to be 1, so that dP by dt plus delta dot gamma is equal to source. Source is 0 because there is no generation or recombination, and in gamma I'm going to enter 2, that is a drift term and the diffusion term. So here it should be holes into mobility of holes and potential along potential differentiation of with respect to x minus diffusion coefficient of holes, the differentiation with respect to holes differentiation with respect to x. You could see over here the conservative flux, the term, the unit, there is no unit error or something. So term is 0 and dA to be 1, Morse coefficient is 0. So we got it. Next, what we're gonna do in the initial values, actually there are two initial values because the holes will be there in the p type and p region, and the holes will be there also in the n region. So I'm going to give another one initial value. I'm going to select the domain of n region and the p region. There are two regions, okay? So in the p region, the amount of holes that are going to be is p naught p, which is the variable I have given already assigned, and the initial values in the n region is NOP, and that's all. We have modeled it, and now we are going to give a boundary condition where I'm going to give the Dirichlet boundary condition. Here the concentration to be Na, and on the other side the concentration is this is from the condition concentration is going to be 10 power of 5 . Now the general form PDE, what I'm going to do is, now we have finished the P region, and the same thing for N region, where the dependent variable is N, and general form PDE, the equation as I said is for N term, so here it changes to be some concentration of electrons into mobility of electrons and potential difference with respect to x, potential with respect to x plus diffusion coefficient of electrons into um, the concentration of change of differentiation of electrons with respect to x. So I'm going to put this in x. You could see over here it doesn't that the unit there is no unit error, and that there is also sum over here 0, and that's it. Here the initial as the same we have to make the initial values in the two regions. So I'm going to select the initial value for the n region. Um, this is the initial values of electrons in the p region, which is equal to p naught n, and the initial values of electrons in the n region, which is n o n. And now the same the like this Z boundary condition I'm going to apply at this end to be donor concentration, which is NB, and here it's going to be 10 power 5. Okay, now we have given the values for the drift and diffusion equation. We have created the Poisson equation and drift and diffusion equation. Now I'm going to mesh this to be let me use the extremely fine mesh, and I'm going to study it. And it says like the maximum number of Newton iterations must reach, and written solution is not converged. Not all parameters are written. So I'm going to this one where I'm going to change this direct to iterative solver, where I'm going to residual tolerance to be 0.1, and non-linear based number of iteration I'm going to increase, and here I'm going to use the non-linear method, automatic highly non-linear, and then I'm going to remesh it, again compute it. That's it. uh, on computing we got the value. This is for potential, this is for C, this is for N, and now we are going to calculate it to be like, let me calculate a line graph. In the line graph I'm going to select everything, and I'm going to calculate the space charge. The space charge is nothing but the value we entered in the Poisson equation, and this is the space charge. This is the source term. The Poisson equation is called space charge, and we're going to insert over there. Okay. And the expression is going to this expression. Let me just got it. That's it. And this is graph 1. Let me do this one. This is the phase charge region, and I'm going to not another one, and I'm going to calculate the electric field. Electric field is nothing but phi x, and I have not selected the path, so I'm not getting any graph. So select it, and not. That's it. It's not. It's an arc length, so I'm going to change it to be the expression 1. That's it. We got the electric graph, and then N-type and P-type concentration profile, and then phase charge region. Thank you so much. We'll meet you next time with a good tutorial on in compound.